all the remaining digits in that card number as well. And we come up with this pretty graph that looks like that, and some of those x's will be the right x's and others won't. So we do the same thing with the second card number, and we get a completely different looking graph because you know, they're just different combinations, and the numbers appear at different places. So what we want to arrive at eventually is the actual map that has a one-to-one mapping between the reordered number and the real card. So we take the intersection of those two graphs. Another slide that took a long time to make. Ready? Ooh. So those are, since you can't tell, they are in bold, but those are the points where the intersections are. And so you know that those are the places that are the real locations, and the other stuff are not. So now that you have this intersection of the mask, and you know, so first of all, you know which locations the digits appear in, and now from this graph, it's going to tell you what the ordering of those digits is. So you can just read it across. The rows, remember, are the position in the original card number. So you take first position, where's the x? 4, okay? First one's a 4, second one's a 0, and just follow the x's over, you know, and you arrive at the original card number. So that was just, you know, obfuscation. It works. We just make sure that it works for the second card number too, and all our work isn't in vain, and it does work. So recap is that, you know, it appeared that there were 10 different mask sequence numbers. So, you know, we talked about 00 through 99. There actually were only 10 of those. So like all the 90s were the same, for example. Once those were determined, any retrieved encoded value from the database could be decoded to recover the original card number. This was just obfuscation, not any form of encryption. The developer had staunchly defended this code for several years, saying that, you know, no one could reverse this. It's safe. I don't need to use encryption. And security through obscurity foiled again. So like I said, that was just kind of a fun example, but you can see how some of the same techniques were applied in terms of analysis. And that is the talk, and I think we have, a whopping 2 minutes for Q&A, and I will be hanging around a little bit afterwards, so any questions?
Excuse me.
Yeah.
Are there any automated tools that can analyze the data, trying to recover the encryption or avoiding compression algorithm using?
Yeah, I mean, if they were using a compression algorithm, the question was, you know, what if there's compression to use as well as the other things? I mean, if it's a standard compression mechanism, you could try running it through some standard things like, you know, a gzip or things like that, but it just comes down to trying some different things until you can get the data into a format that looks like something that looks like something useful. So if you, I mean, first of all, if you put it through gzip and it doesn't throw a big error at you saying this is invalid, then okay, good sign. And you might try that with a number of different compression algorithms. Luckily, in these cases, you know, people don't usually use compression in their cookies, because, you know, you don't really gain that much from it. So it's just another layer that you'd have to deal with. Yeah?
Have you at all tried to automate this process?
If only. I mean, there are certain things that you can do that I mentioned before with regard to kind of looking at where, you know, where there's repetition of blocks, and you can kind of script up things like that. But, you know, every application is so different that finding out where those correlations are is really, really tough to automate. If anybody ever does that, then they're going to make a lot of money. Done? Okay, thank you.